Bismillah and Assalamu alaikum. Now we'll start with the recurrence relations. Recurrence means something that keeps on repeating itself or keeps on coming back again. A recurrence relation for the sequence an is an equation that expresses an in terms of one or more of the previous terms of the sequence. So right now, recurrence relation is not a function at all. It is just a equation which describes the sequence which is a function in terms of its previous values. For example, if you look at the a1, a0, a1 up to an minus 1, so for all integers an, so n naught is a non-negative integer, right? So with n is greater than or equal to n naught, so the an would be described in terms of previous values. For example, we may have a function which says an minus 1 plus plus an minus 2. Now, in this case, any value n is defined in terms of previous values an minus 1 and an minus 2. Now, if you look at these, if I ask a question, for example, what is the value of a0? So we will have to put a0 here, and then we'll have to put 0 n is equal to 0 here, and n equal to 0, and n is equal to 0. So a0 would be a minus 1 plus a minus 2. But we have already decided that n cannot be negative. It starts from 1 or it starts from 0. So this means that we cannot start from n equal to 0. We have to start from n is equal to 1. So let's start from n is equal to 1. So a1 would be described as a. So a1 would be a1 plus a minus 1. So again, we cannot start from n is equal to 1. We have to start from n is equal to 2, which would be equal to n. A2 is equal to a1 plus a0, right? So this means that we'll have to define the values of a0 and a1 in order to start this function. So this thing is called the initial condition. So we'll have to describe the initial conditions for a sequence to specify the terms that precede the first term where the recurrence relation takes effect, which means that the recurrence relation would start from the value from which the previous values define the relation. So a sequence is called a solution for a recurrence relation if its terms satisfy the recurrence. So if you have a sequence which satisfies the recurrence relation, we say that that sequence is a solution of this recurrence relation. So recurrence relation in itself has a solution. The resultant solution would be a sequence which satisfies the recurrence relation. By satisfaction, we mean that the recurrence relation would be basically would generate values of that sequence, and if it generates the values of the sequence correctly, then we say that the sequence is a solution of the recurrence relation. So for example, we have a recurrence relation an is equal to an minus 1 plus 3 for n is equal to 1 2 3 4 5. So here we can start off with from n is equal to 1, because if you put n is equal to a is equal to 0, it would be a minus 1. So we'll have to give an initial condition which is a0 is equal to 2. So what are the values of a1, a2, a3? So we can put in here, for example, it is 2. So 2 plus 3. So the first value would be, what would be the first value? Uh, 5. 5. And then we'll have the next value would be uh, 5 plus 3, 8. And the next value would be 8 plus 3, 8, 11. So first value is 5, the second is 8, the third is 11. So these are the So this sequence 5, 8, 11 is a solution of this recurrence relation. So another example, now we need an minus 1 and an minus 2. So we need two terms, therefore we will have two initial conditions. So we'll have defined a is not is equal to 3 and a1 is equal to 5. So the initial conditions are a is not is equal to 3, a1 is equal to 5, and the next value would start from 2, right? So 5 minus 3 is 2. So the first value would be 2, and then so on and so forth. So you can see that the values are being generated. So moving on, we have a very famous sequence which is Fibonacci sequence. Fibonacci sequence is defined as f0, f1, f2, and here the initial conditions are f0 is equal to 0 and f1 is equal to 1, and the recurrence relation is fn is equal to fn minus 1 plus fn minus 2. So we have to find f2, f3, f4, f5. So it's very easy. You keep on adding them. 0 plus 1 is 1. The next value would be 1. 1 plus 1 is 2. The next value would be 2. The next value would be 1. So see here, 1, 2, 3, 5, 8. So it is a very famous sequence which occurs a lot in nature. For example, the leaves of a tree, and there are many examples. I really am amazed by the fact that this sequence occurs so much in nature. So what does it mean by solving recurrence relations? So in order to solve a recurrence relation, you need to find a formula for the nth term of the sequence generated by a recurrence relation. Such a formula is called a closed formula. So what is a closed formula? A closed formula is a formula which gives us a relation about which gives formula for the nth term of the sequence generated by recurrence relation is called to find. In order to find, for example, if you are given a sequence and if you have to find the relation, and it would be dealt very late in chapter 8, but here is just an example. And so so for example, if you want to start a iterative solution, you start working upward. For example, if an is equal to an minus 1 plus 3, and so you start putting the values here. So ultimately you will get a formula which would be an is equal to n plus 1 plus a, which means 2 plus 3 into n minus 1. So what is happening here is that you are trying to give the recursive relation in terms of the n. So 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 here you don't need any previous value. All you need is to just to find the give the n, and you'll get the appropriate value. For example, if you say 2 plus 3 into n minus 1, for example, if I put 2, what would be the value? 2 minus 1 is 1, 3, 3 plus 2 is 5. So the value would be 5. So if we put here, and that would be how much? 2 plus 3 is 5, right? So this is how what it means to solve a. So a very practical example is the financial applications. Suppose somebody deposits $10,000 in a saving account, and the yield for the per annum is 11%. Now the interest rate is compounded annually. How much will be the account after 30 years? Now one way of finding the value of the account at the last after 30 years would be to keep on finding the saving account value per after every year, and then at the end of the day you would find the. So the recurrence relation is Pn is equal to Pn minus 1 plus 0.11 Pn minus 1, right? So you add 11% to the previous value, and then you get the next value. So 1.1 into Pn. So if in order to find 30, so you'll have to find the 30 terms, and then you would know what is the value of the account at the end after 30 years. So what you can do is instead you can do a forward substitution, and y- you can keep on getting it. For example, 1.1 plus p0, 1.11 p square. So if you will put p2, if you put the value of p1 here, you get p naught into 1.11 square. Here it is p2. So p2 is equal to 1 into 1.11 into 1.11 raised to power square plus p0. So ultimately, finally, we get a value which is in terms of n. So this is a closed form solution. So sorry about the. So we can easily find that 1.1 raised to power 30 and multiplied by 10,000, we'll get the value at the end of 30 years. So this is about recurrence relations, and let me know about how you feel about the video. Thank you very much.